All right. So here we go. So this is week number 3, Thursday. We're going to derive the shearing stress equation for thick wall analysis. And then we're going to do an example. So if you go to Avenue to Learn, I've uploaded some figures in the weekly online lecture notes. If you could download those figures, that'd be fantastic. Okay, so if you could download, that'd be good. So I'm going to so on Tuesday, okay, we start deriving, but I'm gonna start again because it's late. It's too late in the lecture, and some of you might not listen properly. So we're gonna derive this expression over here that I've written, and the root formula, like what we said, the root formula to apply is going to be equal to shear xy is equal to Vy over Izz Qz multiplied by T. Okay. And some of you ask me, Eugene, what is this figure all about? Okay. So if we were to have a shear force coming down over here, right? This is our shear force, and this is our Vy. So in 3D, if I were to sketch this in 3D, how does this actually look like? Okay, so in 3D, you can have a beam, right? So this is our beam. So in a beam, if I were to draw the transformation now, this is our transformation. This is our y. This direction would be our x. Oh, sorry, z. And coming down will be our x. Okay. So the shear force is applied down here is coming down vertically. So this is your Vy. So the phase that we are concerned now, that we are calculating now, is this phase that I'm going to shade, that I'm going to highlight in yellow. So it's this phase that we are seeing now. But the shear stress that we are calculating for is this, okay? So this is the shear stress. So you know this plane will intercept the what? Okay, the plane, the colored plane, the yellow highlighted plane will intersect the x-axis, and the shear stress direction is in the y direction. Okay, so I understand, or you guys already know, the failure is due to the displacement over here, right? So like what I explained last week, the plane are perpendicular to one another, but how will it fail? So the relationship that we have acquired is that the shear in xy is equal to shear in yx. Okay, so to maintain equilibrium, the shear in xy is equal to shear in yx. So in fact, you're not just calculating the shear for the yellow phase, okay, the yellow shaded part. It's in fact transmitted to, oh, bad color. Okay, it's in fact transmitted to this surface also. Okay, that's why we are calculating the shearing stress. Does that make sense to you guys now? Yes or no? Okay, no doubt we are calculating on this phase, right? The phase that I'm coloring now, but it's also transmitted to the perpendicular surface. So the root formula that we're going to use, we already know, is shear stress is equal to Vy over Izz Qz multiplied by T. And we select Izz because Vy is acting perpendicular to Izz. And the first moment of area is also from the ZZ axis. Okay. So like what I stated before I started writing rules for you guys. Yes or no? So we are aware that this is a constant. And it's based from your Vmax. Later on, we'll do a detailed example how to calculate Vy. Okay, so it's not that bad. And then over here, this is your global or entire structure structure second moment of area. And it's also a what? A constant. Okay. Right. So over here, QZ, QZ and T are your variables. So rule number one, I'm going to repeat what I've just the rule said. So rule number one, you have to remember that is that V and I, okay, V and I are constant. Okay, your V and I are constant. Regardless regardless on the point of analysis. Okay, regardless of the point. So this is your rule number one. So the next thing that we want to derive now is the first moment of area, which I've done briefly last week, but I'm going to do it over, okay? Because by deriving the first moment of area, we set out at least 2 to 3 other rules that we have developed, okay, that we're going to develop. So we're going to find the first moment of area. So for this case, we are going to find first moment of area about the z-axis is equal to area multiplied by y bar. Okay, so area over here, I prefer to have a notation that's width multiplied by depth multiplied by y bar, right? So depending on where or how the shear force is acting, okay, so our shear force is coming perpendicularly down. Okay, there's our shear force is coming perpendicularly down. So we know that this will be our width. So when Vy is coming perpendicularly down, it will intersect the zz axis. We are going to take the first moment about the zz axis. So likewise, the geometry that's parallel to the z is going to be the width. Okay, and the perpendicular will be the depth. Okay, so this is parallel to z axis. And the other one, D, this is perpendicular to the zz axis. Okay. So what we are dealing now with is we have this geometry. Let's look at the figure. Y over here is your variable. Okay, Y over here is your variable. So I will define this. Okay, so Y. Okay, Y I'll write down here. Okay, so Y down here is your variable or our slider. So you can move from 0. Okay, you can move from the centroid and go outwards. Okay, and then we have our y bar. So the y bar is the centroid of the area, right, which is a function of y. So if y shift, right, if y shift, y bar will also shift. Okay, so it's the centroid of the area of interest, and the area of interest is the shaded part. So A prime is our defined area. right? And y max or y bar or y max for this case, as shown in the figure, can be equal to C or can be equal to H over 2. Okay. And B for this case is the thickness. Okay. So again, the thickness is parallel to the axis of interest. Okay. Or you can say the thickness is based on the perpendicular geometry direction or geometry orientation relative to the applied shear stress or applied shear force. Any questions so far? You guys are awfully quiet today. Any questions so far, please? So last week on Tuesday, I did not define any of this. Anyone, any question? We okay? Okay. So the next thing that we're going to do now is we're going to write the formula for the first moment of area. So we have QZ, right? QZ or A. So we're going to look at A prime now, right? So A prime is equal to B bracket C minus Y. Okay, C minus Y. And from here we set rule number 2. You set rule number 2. So rule number 2, right? The Y, okay, I'm going to draw the direction of the Y. The Y, this is the direction. This is a slider. Okay, the Y will start from the datum, okay, and move outwards. So these are Y. So rule number 2, okay, by finding the first moment, by finding the area, is the datum of the analysis. Okay, the datum of analysis will start. Okay, not will start. It's at the centroid. Okay, so this is your rule number 2. And what you realize is this bracket over here is C minus Y. Okay, there's C minus Y, and C, like what you see over here, is at its what? Y max. Okay, so C is at its Y max. Okay, it's C minus Y because it's positive. You cannot have Y minus C. You have a negative value. So rule number 3, that we can specify now, is the analysis will start where Y variable is at its maximum. Okay, so this is rule number 3. Okay, and what do I mean by that? So we know that Z is our datum. So the symbol for datum is like this. If you guys do engine drawing, right? That's our Z. But our analysis, when we carry out analysis, our analysis will start when Y variable is the maximum. So this is the analysis direction. Okay, if you do from the bottom bit, right, if you want to consider this area, right, the analysis, okay, direction will be the other way. Oh, Okay. All right. So from here, we already know our area. Then we want to find our y bar. So our y bar is equal to c plus y